Hey everybody, welcome to another lecture in statistics. In this lecture, we're going to be talking about measures of what is average. So apparently there's more than one way for us to quantify what the average of a set of data is. The first method that we have, arithmetic mean, and we can represent this by x bar, an x with a bar over it. We can also represent it by the Greek letter mu. We don't really need to know the distinction between these two things in this course. This actually talks about the arithmetic mean of an entire population. This talks about or refers to the arithmetic mean of a sample taken from a population. In this class, we're just going to use x bar. And to get the arithmetic mean, x bar, we add up all of our data values and then divide by the number of data values that we have. And you might be thinking, well, yeah, that's the average. This measure of average, more correctly referred to as arithmetic mean, is what we're accustomed to thinking of as average. We want the average of a set of data values. We add them all up. We divide by the number of data values. More correctly, this is known as the arithmetic mean. But the arithmetic mean is the measure of average that we're accustomed to. Add up all the values, divide by the number of values. The second measure of what is average is the median. It's the middle data value, essentially. You take all the data values and put them in ascending order from least to greatest. The median value is the middle value. The next measure of what is average is the mode. And the mode is the value that occurs most often. And think about it. When we talk about what is average, one of the things that we sort of associate with something or somebody who's average is that they're typical. Well, maybe that's why we use the mode as a measure of what's average. The mode is the data value that occurs most frequently. And wouldn't we expect what is typical to occur more frequently than the other values? So this is one of the reasons that we use mode as a measure of average or a measure of what is typical. And the last measure of what is average is the midrange. We take all of our data values from least to greatest. We take the least data value, the lowest data value, the highest data value, add them up, divide by 2. And maybe more correctly, instead of saying lowest, we should say least value and greatest value. We take the least value plus the greatest value, divide by 2. Now, why why do we need these four measures of what's average? This is the way that we're accustomed to computing an average. Why can't we just stick with that? And the answer is, none of these four methods by themselves are adequate. None of these four methods of quantifying what is average tell us the whole story. None of these four measures of what is average by themselves consistently give us an accurate perception of what is typical or average in the set of data. If one of these things worked perfectly all the time, we just have that one measure and we wouldn't resort to the others. But all of these have good qualities that the others don't. All of these have flaws that the others don't. None of these by themselves consistently give us an accurate perception of what is typical or what is average about a set of data. We're going to look at the arithmetic mean first. And before we do, I'm going to give some notation that we probably haven't seen. It will be helpful, although not completely necessary, if we introduce a new form of notation. I think that's what this says. I think it says notation. This symbol here is the capital letter sigma in the Greek alphabet. This thing is sigma, and the first letter of sigma, when we spell it, is an S, and S stands for sum. So when we see sigma followed by an X, it represents the sum of the X values. This is just a convenient way of writing the sum of the X values, or the sum of the data values. And as an example, let's consider this set of data values. Here's our set of data values. Sigma X is going to equal the sum of all of these data values. Now let's look at another example. Here's our set of data values. Sigma X is the sum of the data values. 1 plus 2 plus 3 plus 4 plus 5 plus 6. And I sure hope that's 21. Let's say 6 times. Yep, 21. Okay, now we'll get into the first measure of what is average, the arithmetic mean. We now officially define arithmetic mean. Given a set of data values, x1, x2, x3, x4, xn. And notice that there are n of these data values. The arithmetic mean that we denote by x with a bar over it is given by the sum of the data values divided by the number of data values. So we take all of the data values and add them up and divide by the number of data values. This is average as we're accustomed to thinking of average. And sometimes it's a useful measure of what's average, sometimes not. It has its good points, but it doesn't always tell the whole story. Sometimes it does a pretty good job of telling the whole story. Sometimes it can be very misleading. Let's look at some examples. Consider this example. 2 math classes, both have 10 students. On the final exam, the arithmetic mean of the final exam grades for each class was a 70. The arithmetic mean, we add up all the final exam scores, divide by the number of students, which is 10 in this case. The arithmetic mean, what we're accustomed to thinking of as average, the arithmetic mean of the final exam grades for each class was a 70. And so we look at that. For each class, we say, okay, the average final exam score was 70. Okay, so the students in these classes, they're okay. They're typical. They're not real good. They're not real bad. They're just sort of middle of the road, average, typical students. But is that really the case? Let's see. In the first class, here are the final grades. Here are the final exam grades. 70, 70, 70, 70, 70, 70, 70, 70, 70, 70. 10 students, 10 grades, they each got a 70. Well, let's see now. If we add this up, if we do the arithmetic mean, we add up all the test grades and divide by the number of test grades. Add up all of the data values, divide by the number of data values. And wow, everybody got a 70. So that's going to be 70 plus 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 70. 1, 2, 3, 4, 5, 6, 7, 8, 9. Got one more. Plus 70. All over 10. We take 10 of these 70s and add them up. That's 10 times 70. That's 700. Divided by 10 is 70. The arithmetic mean is 70. And when we think of average, we think of, is this typical? In this case, absolutely. All of the students, not bad, not good, right around a 70. And the arithmetic mean is a 70. It's telling us that 70 is average. In this case, 70 is average. It's what's typical of the students. So in this case, in this particular case, the arithmetic mean is a great measure of what's average or typical. We look at that 70 and we think, class average is a 70, the students. Not too good, not too bad, average, typical students. And we're absolutely right. In this case, the arithmetic mean tells us the truth. It gives us a completely accurate perception of what's going on in that class. So that's the first class. Remember, the second class had 10 students, and the arithmetic mean for the final exam grade in that class was a 70 also. Let's see what happens with this other class. We take a look at the second class, and the final exam grades are 100, 100, 0, 100, 100, 100, 0, 100, 100, 0. 10 students in this class, 7 of them got 100, 3 of them got 0. Now, what does the arithmetic mean turn out to be? I think originally, when we introduced this setup, we said both classes had an arithmetic mean of 70. Well, does that work? Let's see. To get the arithmetic mean, we add up all the data values. So we're going to have 100 plus 100 plus 0 plus 3 more hundreds plus another 0 plus 2 more hundreds plus 0 all over the number of data values, 10. And let's see what we're going to get. We're going to get 100, 200, 300, 400, 500, 600, 700. And there it is. The arithmetic mean, the way we're accustomed to computing average, the arithmetic mean gives us a 70. Now, when we look at this 70 and we see class average, we think, okay, class average is a 70. Students aren't too bad, not too good, sort of middle of the road. Typical students. But is that what the individual test scores reveal? We got 7 students here who got 100 on the final exam. So they're probably excellent students. And we got 3 students who got a 0. They did poorly. So can we say that in this case, the arithmetic mean is typical? Not at all. 7 of the students are excellent, 3 of them are very poor. In this case, the arithmetic mean doesn't really tell us anything about the composition of students in the class. It doesn't tell us anything about the test grades other than when you add them all up and divide by 10, you get 70. It doesn't tell us if there were any really good scores there. It doesn't tell us if there were any bad scores there. So all of a sudden, the way that we're accustomed to computing average, that is using the arithmetic mean, shows some shortcomings. It's not a bad method. It's one of the best methods that we have, but it's not foolproof. And it doesn't give us an accurate perception of what's going on all the time. Sometimes it does tell the story, sometimes it doesn't. which is why we have these three other ways of determining what is, quote, average. The next way that we're going to look at is the median, or middle value. Okay, let's look at median, the middle value. We'll look at two cases. We'll look at a case where we have an odd number of data values, and then we'll consider the case where we have an even number of data values. Given an odd number of data values, arrange the data values in ascending order, and there should be a period here. The median is the middle value, the value having the same number of data values above it and below it. Let's see, 1, 2, 3, 4, 5, 6, 7. So we'll note 7 data values odd number. The first thing to do is to take these data values and arrange them in order from least to greatest. Okay, 3 is the least. Then 8, I think, and then 9. So now we ought to be in our teens, and I see 15 and 17. And 26 and 44. Did that get them all? Let's see. We had 7 data values. 1, 2, 3, 4, 5, 6, 7. Okay, that's all of them. The median is the middle value. It has the same number of data values above it. 3 values above. And 3 values below. The value that's in the middle, 15. That wasn't too hard, was it? Now, is this kind of analysis, this kind of way of determining what's average, useful? Maybe. Let's do a couple more examples. We did an example where we had an even number, we did an example where we had an odd number of data values. Now let's talk about what we do when we have an even number of data values and we want to compute the median. Suppose we have an even number of data values and we want to compute the median. Here's what we do. Given an even number of data values, arrange the data values in ascending order. Well, that's exactly what we did when we had an odd number of data values. Arrange them in ascending order, least to greatest. In this case, though, since we have an even number of data values, the median lies between the 2 middle values. If we have an even number of values, there's going to be 2 of them right in the middle. The median lies in between the two middle values. So what do? The median will be the mean of the two middle values. The mean. We add those two middle values together and divide by 2. That's what we do. Now let's look at this set of data values. 16, 26, 33, 12, 16, 55, 41, 16. Let's see, there are 1, 2, 3, 4, 5, 6, 7, 8. Okay. Even number of values. Well, before we worry about even and odd, the first thing we do is we arrange the data values from least to greatest. We do it just like we did with the odd data values. And what's the smallest data value here? I think it's 12. And what's after 12? 16. But we got 3 of them, 16, 16, 16. We list all 3. Okay. So after 16, the next smallest value is 26, and then 33, I hope. And then 41 and 55. Now, it turns out that we have 4 values below the mean and an equal number, 4 values above the mean. We take the 2 middle values, that's what I should put, middle values, and the median is the mean of the 2 middle values. In other words, we add them up and divide by 2, and that's the mean. And son of a gun, the mean really is halfway in between those 2 values. 16 to 21 is 5, 21 to 26 is 5. So this really is halfway in between the middle values. Our mean is 21. Now, is there really any benefit to looking at the median? Oh, whoa, 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 whoa. I misspoke. What did I do wrong here? I put something down that wasn't right. What I computed here was the mean of the 2 middle values, but that's my median. The median is the mean of the 2 middle values. So my median is 21. halfway in between the two middle values. So where I wrote mean here, you erase that, you put median, because that's what we computed. When we have an even number of values, we arrange the data from least to greatest, and then we take the two middle values, we compute the mean. In other words, we add them up, divide by 2, and that's going to be the median. This is the median. Now, is there any value really in computing the median of a set of data? Let's do one more example. Let's take another look at an earlier example. Remember the second class of 10 students? The final exam scores 7. Whoa. Cancel that. Okay. Now I have the correct final exam scores for the second class. 100, 100, 0, 100, 100, 100, 0, 100, 100, 0. The arithmetic mean was 70. Very misleading. We look at the arithmetic mean and think, well, okay, all of the students here, not bad students, not great students, just kind of average, typical students. And yet if we look at the individual test scores, that's not true. We have 1, 2, 3, 4, 5, 6, 7 100s in a class of 10. That's pretty good. And then we have 3 zeros in a class of 10. Ooh, that's not good at all. So the reality is we have 7 really good students and 3 students who are doing poorly. And the arithmetic mean doesn't tell us that at all. It just makes us think that all of the students are average, typical, not too good, not too bad. But what would happen if we computed the median of this set of data? Let's do that. Compute the median. And we arrange the data values from least to greatest. We have 3 zeros, 1, 2, 3, and all the rest are 100s. Let's see, 1, 2, 3, 4, 5, 6, 7. We have 10. We have an even number. 10. Median is the mean of the middle two values. Well, let's see. We take the first 5. These are the lower 5. And then we take the next 5. These are the upper 5. So these are the middle values. The median is going to be the arithmetic mean of those two values. In other words, we add them together, and then we divide by 2, and that's going to give us 100. The arithmetic mean gives us 100. Well, the arithmetic mean by itself doesn't really give us a good picture of what's going on either. If we look at the arithmetic mean and see 100, we think, oh, this is the middle value? This is a very good class. All of these students must be excellent if this is the middle value. And that's misleading too. But what would happen if we took the arithmetic mean and the median and used both of these to tell the story? The median says the middle grade is 100. And yet the arithmetic mean is a 70. Well, wait a minute. If the middle grade is 100, something really had to happen to drag this mean down from 100 to 70. And then all of a sudden we figure out, okay, you know what? If the median is 100, then we've got a lot of really high grades here, a lot of 100s, a lot of really high grades. And then we must have a couple of poor grades that drag the arithmetic mean down to a 70. And this is oftentimes why we use different measures of what's average. None of them by themselves tell an accurate story. But when we put two or more witnesses together, then we see what's really going on. So this is one witness, this is another witness, and each of these witnesses fills in the blanks that the other witness can't tell. Put them together, and they tell us exactly what's going on. So this is why we have different forms or different measures of what's average. Next, we're going to be looking at mode. The third measure of what's average or what's typical is the mode. We're going to be computing the mode of sets of numerical data. I think in practice, the mode is mainly used to determine what's average or typical if we have data that's not numerical. For example, if we survey 10 automobile owners and 3 of them have Fords, 2 of them have Honda, and 1 of them has a Chevy, and 1 of them has this, and 1 of them has that. Ford, because it occurs most often, would be the mode. Now, you can't take Fords and Chevys and Hondas and Subarus and Kias and add them up and compute an average. How do you add a Ford and a Kia, divide by 2, and come up with an average? You can't. So when we have non-numerical data, like the names of automobile manufacturers, the mode is going to be what's typical in the sense that it occurs more often than the other pieces of data. But just for the sake of illustration, we will work with sets of numerical data. The mode of a set of data is the data value that occurs most often. If 2 values are tied for the most occurrences, then we say that there are 2 modes. In this case, the set of data values is bimodal because we have 2 modes. Again, if we were doing automobile manufacturers and we surveyed at random 10 automobile owners and 3 of them had Fords and 3 of them had Kias, and then the other 4 automobile owners own different brands of automobiles. In that case, we have 3 Fords, 3 Kias. The set of data would be bimodal, and so there would be 2 modes, Ford, Kia. And this would give us an idea of what's average or typical as far as types of automobiles that people own. But that's the last time I'm going to mention data sets that aren't numerical. We're going to talk about mode, and we're only going to give consideration to numerical data. The mode of a set of data is the data value that occurs most often. If two values are tied for the most occurrences, then we say that there are two modes. In this case, when there are two modes, the set of data values is bimodal. We have a set of data values here. Let's find the mode. And one thing that probably jumps out at us is that we have a few 16s here. Does any other number occur more than once? We have, let's see, 1, 2, 3, 4, 5, 6, 7, 8. 8 data values, and 3 of them are 16s. 26 occurs once. 33 occurs once. 12 occurs once. 55 occurs once. 41 occurs once. But 16 occurs 3 times. Three occurrences. And I sure hope there are 2 R's in the word occurrence, but I'm beginning to doubt it now. The data value that appears most often is 16. Another example, find the mode. There are 7 data values here. 14 occurs once, 28 occurs once, 19 occurs once, 57 occurs once, 42 occurs once, 35 occurs once, 76 occurs once. None of these data values occur more than once. So in this case, can we really say that there's one data value that occurs more than all the others? I'll tell you what we're not going to do. We're not going to say, all of these data values are tied for first place since each of them occurs once. So they're all modes. No, we're not going to do that. If we have 2 data values that are tied for first place, we'll say that both of them are modes and that the set of data is bimodal. But if we have a bunch of data values and none of them occur more than once, we just say there is no mode. One more example with modes. I've got a set of data here, and I guess there are about 10 values. I don't have to write these values in ascending order, but I think I will because there are enough values here that I'm not really sure what I'm looking at. So I'm going to arrange in order from least to greatest. And is there anything less than a 14 here? I don't think so. So I'll just mark that out. We have 19. Is there anything less than 19? No. And 19 occurs once, twice, 3 times. So I'll write down those 3 19s. And I'll also draw a line through them so that they won't distract me. As a matter of fact, I think I'm going to erase the ones that I've already used. And everything else will stand out a little bit better. The smallest value now is 28. And I've got 3 of those. Gone 128, gone another 28, gone a third 28. And none of the remaining values repeats. I have 37, 46, and 57. So this is my set of data arranged from least to greatest. And wow, I got 3 19s, 3 occurrences, and son of a gun, the word occurrence actually does have 2 R's. 3 occurrences here. So 19 and 28 are tied for first place. The data set is bimodal. One mode is 19. Another mode is 28. Last but not least, we'll look at our 4th measure of average. The last measure of what's average or what's typical, the mid-range. The mid-range of a set of data values is given by the least value plus the greatest value over 2. So we're computing the mean of the least value and the greatest value. Let's look at a few examples. Mid-range, our last measure of what's average or typical. The mid-range of a set of data values is the mean of the least value and the greatest value. We add the least value and the greatest value together, divide by 2. And as our first example, we're going to go back to the 2nd class final exam scores. We've computed the mean, we've computed the median. Now we're going to do the mid-range. Least plus greatest over 2, and that's going to give us 0 plus 100 over 2, which is 50. Mid-range is 50. Well, we look at this and we think, my goodness, this has to be a terrible class. This is the middle? Oh my goodness. But remember what the median was. The median was 100. And the mean, the arithmetic mean x bar, was a 70. Wait a minute, the median was 100? The middle score was 100? The score in the middle was 100, and yet the mid-range was 50? And the mean was 70? Not only did we have to have some low scores, but wait a minute now. We know what the highest score was. It was 100. The lowest plus the highest divided by 2 is, we had some zeros there. Okay, we put these three measures of what's averaged together. And now we got three witnesses testifying, and there are no holes left in the testimony. Nothing for the investigators to figure out. Based on these three different measures of what is average, we have a really good idea of what happened on the final exam without having to look at any of the individual test scores. Now, in a case where we have 10 test scores, well, we might as well look at the scores, and that'll tell us. But suppose we have, instead of 10 test scores, we have 2,000. Even if we look at all 2,000, there are going to be so many scores here that we're not going to be able to tell what happened. But these three measures of what average is will give us a pretty good idea. So if we have a lot of data values, we can look at those data values, and there will be so many of them, we won't have a clue what happened. But if we look at different measures of what average is and let each one tell their own story, we can get a pretty good idea of what happened and what is average in that particular class. Let's look at another example. Let's look at the first class final exam scores. The mid-range is the least plus the greatest over 2. So that's 70 plus 70 over 2, which equals 70. The mid-range, 70. The median, 70. The arithmetic mean, x bar, is 70. These three witnesses testifying together make it pretty clear everybody in the class got a 70. Now again, there are only 10 test scores here. But suppose there were 10,000. We don't want to look at all 10,000. And even if we did, we might not really know what's going on. But we look at these three different measures of what's average, and we say, okay, it looks like just about everybody got a 70. So this really is a class of average or typical people. Not too good, not too bad, kind of middle of the road. These three measures of average combined give us a pretty good idea of what happened. One more example. You may or may not remember, but we've seen this set of data before. It wasn't related to test grades or anything. We just used this as an example when computing the median. Now we want to compute the mid-range. And so we'll have the least plus the greatest all over 2. 12 is the least. 55 is the greatest. And that's 67 divided by 2, so that's 33.5. And you might remember when we were doing the median was 21. Okay. For homework, we have, I don't know, about 5 or 6 examples. we got to do range, we got to do mid-range, we got to do median, we got to do mode, we got to do arithmetic mean. So have at it and enjoy it.